Okay, now we're recording for the online folks. So today, what we're going through is pure substances and mixtures. We're going to start with pure substances. A pure substance is a substance with a defined chemical composition. So I can actually write out the chemical formula for this. For example, a pure substance could be H2O. There might be some other chemicals if it's like water that's coming out of the tap. But if it's pure water, that is the formula, and it doesn't change. That is a pure substance. So if you can write out a chemical composition, if you can write a chemical formula for it, that is a pure substance. Their example: aluminum, just regular oxygen, O2 that we breathe in the air. Water, H2O, like I wrote on the board. Glucose, which is a bigger chemical formula, but still a pure substance. What is glucose? Sugar. And the formula for sugar is C6H12O6. So 6 carbons, 12 hydrogens, 6 oxygens. That is your defined formula. If you change it into something else, it's no longer glucose. It's sucrose or whatever other kind of sugar it might be. So an element, as defined, is a pure substance consisting of only one type of atom. So their example on the other page was aluminum or oxygen. That only has one atom from the periodic table. It's not like a compound molecule where you have hydrogen and oxygen or carbon and hydrogen and oxygen. It's just one thing, oxygen or aluminum or whatever it happens to be. All known elements are listed in the periodic table, especially if you have an up-to-date one. If you have an old one like I have in the closet, they might have some blank spots down here at the bottom because we've been discovering new ones. Not anytime recently, but you go back 30, 50 years and we didn't know about all the elements that are down here at the very bottom. We'll get to this later, but the ones at the very, very bottom are more radioactive. Some of them decay very, very quickly, and so they really only exist for a couple seconds at a time, like in a super collider or something. So they're very, very volatile, and it took us a long time and a lot of technology to be able to figure out that they're there. Some elements appear as single atoms. Some elements appear in groups of two. These are called your diatomic elements, and I took it down to, because they painted the rooms, the whole school really, last year. I have a piece of paper, and I will have it taped to the wall. Sorry it's not up there today. That has all the diatomic elements. Basically, there's some elements that just they will not hang out by themselves. Oxygen is one of them. When we talk about oxygen in the air, what's the formula we say for that? O2. It's never O1. There really is no O1. That would be extremely reactive, and it would only take just a couple seconds or probably less than a second for it to find another atom to connect to, and it would either be O2 or it would be something else. And so these elements really do not appear in groups of one. I think there's only 7 of them. 1, 2, 3, 4, 5, 6, 7. Boom. That's right. So hydrogen is one of them. There is no H1 naturally in nature. We can make it happen. But in general, hydrogen comes in pairs of 2. Nitrogen comes in pairs of 2. Oxygen, fluorine, chlorine, bromine, and iodine. Those are your 7. And so they show their molecules here. Note that as you go up the periodic table, and we will spend plenty of time talking about the periodic table, note that as you go up the periodic table, your atoms get bigger and bigger and bigger. So hydrogen is the first element. It's also the smallest. Nitrogen is smaller than oxygen, it's smaller than fluorine, and it just keeps getting bigger and bigger and bigger as you go up the periodic table. Some elements exist in multiple forms. Their example is carbon. Carbon can exist as graphite, which is like in your pencil leads, although that's probably not, I don't know if they use just straight graphite anymore. They might use some other chemical compound. But graphite's used in pencil leads, it's used in lubricants, it's used in all sorts of stuff. The other more commonly known form of carbon is diamonds. Those are both pure carbon. It's just carbon is attached to each other in different ways. So they're 2 different types of carbon. Let's see. A compound. So we talked about a pure substance. We talked about an element. Now we're going to talk about a compound. A compound is a substance formed from two or more atoms of different elements that are chemically combined. So it's not a mixture. We'll talk about a mixture in a little bit. But a compound would be like water. You have two elements, two or more atoms, hydrogen and oxygen, and they are chemically combined. They don't really come apart. You're not ever going to see water just not become water. They have a chemical combination there. It's a fixed ratio. If it's water, it's always two hydrogens and one oxygen, H2O. You can't have HO2. Well, you can. It's not going to be water. It's going to be something else. So, and we haven't really discussed these yet. We'll spend plenty of time on these. The bonds can either be ionic or covalent. Basically, ionic has a charge, and the charges attract each other. Covalent, you're sharing electrons, and they're bonded a little bit more strongly because they have an electron that they share between each other. A formula unit is the most basic unit for your chemical. So like H2O, that is your basic unit. The formula containing the lowest whole number ratio of atoms. I cannot reduce H2O. I could cut the hydrogens in half and only have one hydrogen, but I can't cut an oxygen atom in half. One is the lowest number I can have as far as atoms. You can't cut them into smaller pieces than that. And so H2O is as low as it goes. Now, I could have something like, if I'm doing some math and I'm trying to figure out an unknown chemical, I might come to the conclusion that it's H4O2. This can be reduced. I can divide both of these by 2, and so this would not be the formula unit. This would be a different term, but the formula unit is just going to be your lowest whole number ratio. You don't write the 1. The 1 is implied. H2O. So the molecule for some things are bigger. For example, I don't know if they're about to show this. Glucose. The formula for that was C6H12O6. Can I reduce 6 and 12s? What would I divide by? I divide by 6. That would be the best one. So C1H2O1. You don't really have to write the ones. This would be the formula unit. Let me bring my computer over here. The online people are like, what's he doing? What's he talking about? And you don't need to know about street plates. So CH2O would be the formula unit. That's the lowest whole number ratio. But this is not sugar. If you take one of these molecules and put it in your mouth, it's not going to taste sweet. It's something completely different. And so C6H12O6 is your actual molecule. And these things can be different. The whole reason we have a formula unit is sometimes it's easier to work in this if you're doing math, if you're trying to weigh things out, or if you're trying to discover an unknown solution, like if I give you a pile of sugar and you're actually doing something in the lab with it and trying to figure out what it is, you might come to this conclusion here, but this is not your actual molecule. This will be your molecule of sugar. If you change any number of atoms in a molecule, you're going to create something else. If we have a chemical formula for glucose, and this is the chemical formula, you can't go any higher or any lower in your actual molecule and still have the same substance. Make sure your mask is above your nose, especially if you have a runny nose and are sick. So, there's your molecule. Not always the lowest whole number ratio, like I showed you with the glucose. Compositions of pure substances are described by their formulas. Subscripts. Sorry, my brain freaked out for a second. The subscripts are the little tiny numbers that are wrote over here. So script means like writing. Sub means below. And so the little numbers down below are your subscripts. We do use them actually. If you go into numbers in scientific notation, the exponent here, if you write this in a computer, like if you try to put exponents into Word program, these are called superscripts. So sub is below, super is above. Just kind of remember that. We won't call them superscripts too much. They're exponents in math. But that kind of helps you remember that the sub is below, the super is above, and scripts just means that they're words. So subscripts represent how many atoms of each element are present. So H2O, the 2 goes with the H, not with the O. And we all know that. The number goes after the element that it's representing. You can have bigger numbers, which I don't know if they get to just yet. But they talk about the formula here: 12 atoms of hydrogen, 6 of oxygen. Subscripts are written after the symbol of the element. Note that you don't write the 1. We don't say H2O1. It's just H2O. If there's no number written there, you just assume that they have 1. I'll talk about that later when we actually get to it. So, properties of compounds are different from the properties of the element that combine to form them. Sugar has oxygen in it, right? Can you breathe sugar? Like if you get into a vat of sugar, you can't breathe it. No, you're gonna drown or you're gonna choke if it's solid sugar, not liquid. And so it has lots of oxygen in it. That's not oxygen that you can breathe like O2. And so just because something has it in there doesn't mean that it retains that property. The properties are different. And I think in the video that I showed you at the beginning of the year, he talked about how you can have poisonous elements that by themselves are poisonous. If you take them in, if you eat them, they're going to kill you. But you might look in the formula of like a medicine, a life-saving medicine, and it could have individual elements that by themselves are poisonous, but combined together in that entire formula, they're actually good for you. And so know that in a compound or a molecule, each individual thing doesn't retain its proper stuff. One of the best examples is salt. You literally need salt to live. Don't go eating a bunch of salt because you'll find out, hopefully in health class or in nutrition, everything today has way too much salt in it, and you don't need any extra salt. But back in the day when we just ate vegetables and meats that came straight from the animals when they weren't seasoned or anything, salt was worth more than gold. Because gold's nice and everything, but it's not going to keep you alive. Salt will literally keep you alive. Hence the phrase, if you've ever heard it, worth his weight in salt. That's because salt was very, very expensive. It was very expensive because it would keep you alive. Now, together, sodium and chlorine make salt. They make your fries delicious. They make your meat delicious. Salt is nice. If you have something that tastes bland, throw some salt on it. Separately, each of these will kill you, very quickly. Sodium is a highly reactive metal. When it comes in contact with water, it literally explodes. And your body is 90-something% water. So you eat straight sodium, you're going to die, a horrible, horrible death. Chlorine, it's a poisonous gas. Not good for you either. So each of these separately will kill you very quickly and not in a fun way. Put them together with nice salty fries and potato chips and deliciously seasoned steak. And you literally need it to live if you don't eat enough salt. Which again won't be a problem for any of you today in today's society, but you need salt to live. It is a basic component of what you need. That's why your Gatorades are all salty, because when you sweat a lot, you sweat out all your salt, and you need to replenish that. You need the electrolytes. Let's see. Law of definite proportions. The law states that certain chemical compounds will always contain the same ratio of elements. H2O will always have 2 hydrogens and 1 oxygen. If you add another oxygen, you have something completely different. This is H2O2, or hydrogen peroxide. So the same amount of hydrogens per oxygen. Anybody know what hydrogen peroxide is? It's the stuff, you put on your cuts. You don't want to drink hydrogen peroxide. Again, not going to be good for you. So you got to maintain that same ratio of elements. There's a law of multiple proportions, which states that if multiple compounds can be formed from the combination of the same elements, then the formulas of the resulting compounds will have a small defined whole number ratios. I don't know if they give an example there. One of the examples is hydrocarbons. So when we talk about gasoline, they all have similar names. Propane, ethane, methane, I forget all of them. Octane, like the octane in your gasoline. Those are all some combination of hydrogen. So this is methane. I think octane would be C2H8. Propane might be 6. I don't remember all of them off the top of my head, but they're all some sort of combination of carbons and hydrogen. which is why we call them hydrocarbons. Everybody make sure that you're awake. Go lights on. Now, the last one, I think we're nearing the end, is a mixture. A mixture is different than a chemical compound because you can unmix a mixture. Their example for a mixture is going to be like trail mix or sugar water. I can mix the sugar in the water. It's going to dissolve. The sugar is still the sugar. When I drink the water, I'm going to taste the sweetness of the sugar. When I drink it, I'm also going to get the hydration of the water. That's why we love Kool-Aid. If I were to try to separate this, I could separate the sugar out from the water. I could just evaporate the water away, and it would leave all the sugar behind down in the bottom. Same thing with salt. Air is also a mixture. It's kind of hard to unmix it, but we pull different things out of the air. One of the ways we're trying to combat climate change is build big machines that pull CO2 out of the air, that pull methane out of the air to keep those greenhouse gases from affecting the environment. So we have two different types of mixtures. We have a heterogeneous mixture, which basically does not have a uniform color. So these are the same hetero and homo that we use to describe sexual orientations. So hetero means different, homo means the same. A mixture that does not have a uniform composition, their example here is going to be trail mix or oil and water. You should know that oil and water don't mix. So you pour them in the same glass, they're going to look different. Where you go to homogeneous mixtures, homo means the same. So a mixture that has a uniform composition or phase solution. Their example here is what? They don't even tell us. But you can see that you don't see two different things in this vial here. Where here you clearly see the water and the oil. Here you have some sort of mixture, which they don't really tell you what it is. My example would be sugar water. When you mix the sugar in the water, you don't see the sugar. It's just there dissolved in it. Same thing with salt water. If I gave you a glass of salt water versus regular water, could you see the difference between the two? No, those are homogeneous mixtures. They look the same. So with mixtures, you do have a certain ratio, but it's not really defined. So like if I say trail mix, some people are like, yeah, it better have a lot of peanuts in it. And some of y'all are like, no peanuts at all, just like chocolate and M&Ms. I don't know what else you'd put in the trail mix besides peanuts, but some people don't like peanuts. Or maybe you're allergic to peanuts and you want like a non-peanut trail mix. But yeah, you do have a ratio. It's just not defined. It can change. The properties of a mixture are a blend of the properties of the substance they are made from. Like I said, with the sugar and the water, you mix those together. You still have sugar. You still have water. They don't become something new. They retain their same properties. Let's see. Compounds can be separated by chemical processes. We can go into the lab and separate different compounds out, but it requires chemical reactions. It requires a little bit else. Mixtures can be separated by physical processes. I can take trail mix and go in and pick out all the peanuts if I don't like the peanuts, and then just eat whatever's left over in my trail mix, which I guess would be like M&Ms and raisins or something like that. Depends on what you have in there. So you can filter out different things from a mixture and physically separate it. Or like I said with the sugar water, you can distill it so you can evaporate all the water out and leave the sugar left over. And then they do have chromatography for some things. Basically, you're using light to separate things out. Basically, the difference in particle sizes, separation of purple marker into red and blue dye when wet. So, yeah. Uniform, not uniform. This is kind of like a flow chart that shows you whether you have an element, a compound, a heterogeneous mixture, or a homogeneous mixture. So I will actually leave this one up because that's the last slide. You can go ahead and get started on the assignment. It shouldn't be too long. But if you have any questions, let me know or send me an email, and I will get back to you. Have a nice day.